So we've reached a point where the electron moves from just a little charged particle, which is causing electricity, and we've moved now into the realm of modern physics, Einstein, and all the rest of that. Einstein actually won his Nobel Prize for the explanation of the photoelectric effect. Relativistic effects and all that sort of thing. I can't even say it. And they couldn't understand it. I barely understand it myself, 50 years into studying the damn stuff. But definitely, it's tough stuff. Whereas the photoelectric effect, much easier. I can explain that, and I'm going to do it now. We have to start off with X-rays. Now, basically, X-rays are where tiny little particles called electrons jump off of a cathode ray tube's cathode and get accelerated towards the anode. Now, all this happens in a vacuum chamber. You've got to have a vacuum. That's a vacuum inside there, and surrounded by a fairly healthy piece of lead shielding, which goes all the way around except for a little space down here where the waves come out. Now, as the electrons hit the metal, the energy of the electron gets turned into a wave. And the waves, let's go for a different colour, go back for red. The waves come down the tube. Now, remember, these waves are photons. They are a small piece of energy, not an entire wave, but a small piece of energy, as energy always comes in pieces. And these waves are in pieces called photons. And they are very high energy photons because they're made from X-rays. But one of the most important things is that one electron creates one photon. You can't have two electrons creating one photon or one electron creating two photons. Either way around is impossible. Every time one electron goes to one photon. So, electrons leave the surface of the cathode by thermionic emission. They're then accelerated by the high energy field, which is created by a high voltage, a very high voltage. High tension, we say. It's an old-fashioned word, but we still use it sometimes for mean a very high voltage. Now, 90% of the energy of these electrons gets turned into heat. They basically don't hit an atom in the right way to create an X-ray. But when they do, the X-rays formed are very high energy photons. They are very penetrating. They fog films, and they are not affected by electric fields. These are called the properties. This is the properties of the electron, meaning what they can do. The uses are different. The uses, of course, of an X-ray and an electron, but an X-ray in this case is to detect things which are hidden to us. Imaging, the inside of the body, and also can be used in certain forms of treatment. Guess what you can use to treat them with? Now, how does all this work? Well, Niels, was the first to suggest that atoms basically weren't clouds like a solar system, that the electrons are in energy levels. And what was basically happening was that there was a change in energy levels from electrons. They didn't stay at the same energy level. In fact, when you gave an atom any kind of energy, the electron will jump into a higher level. Not its ground state, but a higher level, which we say is excited. The electron gets excited and it jumps to a higher energy level. Now, it doesn't stay at that energy level. It comes back from that energy level to the ground level. And when it does that, it has to lose the energy it had in the higher energy level. It has to lose it. And to do that, it gives out a photon, a small piece of electromagnetic radiation, an electromagnetic wave. Now, because the gap between the two is always the same, then the size of the photon is always the same. And we can calculate that using this formula. The difference between the two energy levels gives us the frequency of the photon produced. And this is the gentleman. There he is. That's Max Planck. Now, all over Germany, you have Max Planck Institutes, which are really famous. He didn't actually found them. They kind of named him after him because, like a lot of other scientists at the time, they kicked him out for being Jewish. But Max Planck basically came up with this basic idea. It's a hugely important idea. There were three scientists, I'd say, that we sort of like hinged the theory of all modern physics on. Max Planck with his idea of unit energy. Then there's Einstein with his idea of energy converting to mass. And finally you have Dirac, who managed to work that into the modern world and into actual useful phases with his ideas of antimatter and other things. Well, Dirac did so much work, it's almost impossible to note it all here. So in the modern world, you have these three guys, just like in the ancient world, you'd have had Newton, Faraday. I'll say ancient, but it's old enough. You know, Faraday, Maxwell, those people. And they are revolutionary thinkers. And by studying what they did, we can understand a bit more about how science has changed. And one of the ones who is perhaps least known, certainly with Dirac, would be Max Planck. Max Planck's idea is that all energy came in small pieces, and these pieces were generated when an electron came from a more excited state to a less excited state and generated a photon. Very important piece of understanding. Now, how much energy, and so what is the wavelength of these X-rays? Well, we saw in the last section in part 3, which if you haven't watched, then this is all going to be difficult for you, so stop it here, go back, watch part 3 and then do this bit. That is how much energy we gain going through an electric field. Now, if the electric field has a 2000 volt potential difference, then that's the energy you gain. It's the charge on the electron, that's the charge on the electron, times the 2000. Now, Planck, on the other hand, said that you can find out the frequency by using a formula of a constant, which eventually got called Planck's constant. He didn't call it that, he just called it the universal constant. Planck's constant times the frequency. That is Planck's constant. There it is. Now, I've just seen this should be 10 to the minus 34. It's 10 to the minus 34. How long have I been using this? Oh, God almighty. Anyway, to convert frequency to wavelength, we use the formula frequency equals the speed of light over the wavelength. So I've just put that in. You'll have to take my word for that. When we do waves, I'll explain that a bit more. Now you have to do the maths. I want you to find the wavelength. Do it now. Stop this. Do it now and find out what you get, because that's quite important. The wavelength of an X-ray. Now, it should be less than the wavelength of light, which is around 6.4 times 10 to the minus 7 meters. So it's got to be big, it's got to be a bigger minus than minus 7, is basically what I'm saying. And what does all this mean in terms of what we can actually see in life? Well, if something's a black body, which means it'll generate all different types of frequency, it's a perfect transmitter. You know, black is beautiful, basically. Black is a fantastic transmitter of any sort of radiation. Electromagnetic radiation in particular we're dealing with here. Now that's any normal object's a black body, but monoatomic gases which are incredibly simple, they have one atom sitting on its own and just have a very limited number of spaces and jumps that the electron can do. And each line you see on a line spectra you're looking at below, this represents a jump. For instance, this one here. This represents a jump when an electron has gone down from one energy level to another. So this is maybe 6 down to energy level 5. It's done that jump and it's emitted that light. It's emitted exactly that frequency, which is why you get a line, because only that frequency is being produced. Now, as atoms get more complicated, there's all sorts of bonds and things. There's so many possible jumps that you end up with something looking like that. But if you have very simple systems, such as we can see here, potassium, this is potassium here, it will only have a set number of lines because there's only a set number of jumps that are possible. Jump up because energy absorbed, fall back and give out this radiation when energy is emitted. So here's another representation of it. You can see the different colours represent different jumps. The red jump, as you can see, is a shorter fall back. So you have all different excited states. Now, none of these are going back to the ground state. They're all going back to a lower excited state. Anything is possible, as you can imagine, with all these physics. There's less regard. But the distances, the energy gaps between these orbitals, these energy states, is set. So the colour will always be the same. And this is why when we heat up sodium, it glows yellow, because that is a particular electron jump. It's a very prominent one in the element, and so it always will glow yellow, and it's always the same frequency yellow because it's the same gap, it's the same electron fallback that we're looking at. So here's the red one, the, I don't know what you call that, is that green? Turquoise, and then the blue one, and they're all different falls back because they represent different gas. Now, if you heat a gas, therefore, you get an energy emission spectrum. If you pass white light through a cold gas, it will absorb light. This is the dark lines here are where the energy is being absorbed, and notice they are at the same points as the hot gas generates. So the absorption spectrum is essentially the same as the emission spectrum, but in reverse. Now, this is actually how we detected the gas helium. Helium was detected in the atmosphere of the sun because it had an absorption spectrum different from anything else we found on Earth. And it's called helium because we thought it was only associated with the sun. Okay, so back to Einstein again. Einstein had been plugging away, doing his thought experiments, impressing about, well, maybe 100 people at best in the world who understood what he was talking about. I think 100's being generous, actually. And then the big problem came up. A big problem that ended up causing quantum mechanics. And he, like me, is an old world Jew, and he couldn't really accept quantum mechanics. I have a bit of trouble with quantum mechanics myself. So, what was the problem? Well, a long time ago, people found out that just like heat causing electrons to jump off a metal, if you shone light onto a metal, electrons always jumped off. This is not surprising. Both light and heat are forms of energy, and they give their energy to the electrons, and the electrons jump into space. And it got called the photoelectric effect. Now, we can prove the existence of the photoelectric effect using a charged electroscope. That's a device which detects static electricity. So if you charge it up so that the gold foil plate and everything are prominent, sticking up, and you know it's charged negative, and then you shine a UV light onto this zinc plate, that's the UV light there, that's the UV light, the leaf immediately collapses, as you can see. It's gone. It's discharged. Now, nothing's touched it. The UV light has discharged it on its own. So what's happened? Well, of course, what's happened is the UV light has caused the photoelectric effect. The electrons have left the metal plate, bombed off into space, and without those electrons, the electroscope isn't charged anymore. So, when the UV light is shone on the plate, the leaf collapses and all the electrons leave the surface of the zinc. Now, we can use this in a photocell. This is a basic photocell. You've got a plate which sees light coming in. There's light coming in here. Light's coming in from some source onto the plate here. Electrons jump off that surface by the photoelectric effect, and then they get accelerated across the gap there by this battery down the bottom. It doesn't have to be very high. It's not going to be, we're not looking for huge acceleration, but they will be accelerated by the difference in potential between this. So this makes this the cathode, and this makes this the anode, as you can see. Right, so electricity is forced across the plate by the presence of the electrons, by the presence of the battery, sorry. And you can detect the flow using the ammeter. And the more light, the more electrons, the more the flow, the ammeter. So you get a way of measuring light. And in fact, if you introduce a bulb, to it, you can see the ammeter, and if you move the bulb further away, the amount of flow, the ammeter reading, will decrease. That's just because of distance. You've just reduced the amount of the intensity of the light by moving the bulb. This is actually a question. They actually asked this: how do you change the intensity of the light? We just moved the bulb further away. That was the actual answer. Right, so photoelectric effect, lovely. You get more current for more light intensity. Light intensity really is the number of photons, the number of little pieces of electromagnetic wave which are hitting the plate. And the current, well, that's just the number of electrons. And they're directly related to each other, which is what I said. One photon creates one electron is the result of being hit by one photon. And the other way around for X-rays. It always is a 1-to-1 ratio. And this is kind of what Einstein already understood, and why he never had any problem with the photoelectric effect that other people couldn't understand. Because though this is perfectly understandable, and the use of the photocell had already started, people were using it for light meters of cameras. Burglar alarms, a little sensor when they shone a laser across, and you have to go around the laser like in Mission Impossible. Though, you know, it's much easier for Tom Cruise, being as very short he is. The light is detected using a photocell. Problem. So what was the problem that Einstein had to solve? Well, the problem is frequency. It's all very well when you change the intensity, but if you change the frequency, you get a very strange effect indeed. For below a certain frequency, you get absolutely nothing. You don't get the photoelectric effect. It doesn't happen. Electrons do not leave the surface of the metal if the light's the wrong frequency. Now, you can shine a red light on zinc as strong as you like, something that would blind you, and you don't get the photoelectric effect. Whereas the weakest ultraviolet, like something you get from a battery torch, you know, that you can produce on one of those tiny little battery UV things that they carry around in clubs. The smallest one of those will create the photoelectric effect. And explaining this was difficult because it didn't fit in with Newtonian physics. And Newton was the god. He was the man. And everybody said Newton was perfect. Well, he had already proved he hadn't been perfect, but he was perfect up to now in energy and forces because of his understanding of mathematics. But this didn't fit with Newtonian physics, and it needed an explanation, and along came Einstein with that explanation. You see, Einstein said that instead of it just being the photoelectric effect being electrons ejected from the... That was the word I was having trouble with, by the way. Electrons being ejected from the surface of a metal by incident electromagnetic radiation. Now, it says in some books, it says light, but you must say EM radiation because it's much more correct. Electromagnetic radiation of a suitable frequency. It's got to be the right frequency. So he changed the definition of what the photoelectric effect is. Then he said, right, energy comes in packages. Planck said that. One package, i.e. one photon, hits one electron. If that package is too small for the electron to leave, then it won't leave. If you have very strong red light, the packages are very small. They hit the electron, no luck at all. Here, I've compared green light, that's green, with UV light at the bottom here. Now, the green light has a small package and will only get the electron that far up the energy grid. It can't leave. It hasn't enough energy. So it gets hit, it gets hit, it gets hit, it gets hit, but it never gets enough energy to leave the metal. Whereas UV light, with a much higher frequency than green light, hits one electron, immediately gives it all its energy, and it leaves. Yes, there it is. It's gone. So, the UV light has given more energy because it has a higher frequency. So the size of the amount of energy in the light is not to do with how much or brightness of it, its intensity. That just tells you how many photons there are and how many electrons can be stimulated. The energy that the electron gets is only dependent on the frequency of the electricity. So, here is Einstein again. This was his mathematical explanation of the law. He said that the basic frequency, the smallest frequency that will generate the photoelectric effect, he called it the threshold frequency. And he came up with a mathematical explanation. He said that the threshold frequency, as you can see at F0, being the minimum frequency, that's the smallest energy you need. So, if your incident radiation, if your incident photon is bigger than the threshold frequency, has more energy than the minimum, then it will push an electron out. Now, we've got a name for the minimum amount of energy. We call it the work function. That's the minimum amount of energy. But it's simply the Planck's constant times the threshold frequency. So if your incoming frequency is bigger than that, you get an electron. If it's smaller than that, you don't liberate an electron. So anything left over, by the way, anything which isn't used in liberating the electron, any leftover energy must be turned into kinetic energy, because the electron can only carry kinetic energy. So the leftover energy gets turned into velocity in the form of kinetic energy. And you can work it out, of course, using a half mv squared. So this formula, which of course is in the log tables, is the basis of Einstein's explanation for the photoelectric effect. And just to go over it one more time, he said that one electron is generated by one photon of energy, and only if that photon of energy has a high enough frequency can it liberate the electron. So here are the questions set. This one, quite a nice one, doesn't take you very long. A little bit of a calculation down at the bottom. Here's EV. Don't forget how to convert that into energy. You just times the voltage, which is 4.3 in this case, times the charge on the electron. And here's another one here. This one has a slightly longer thing. It starts with your voltage, the voltage of the X-ray tube, and asks you for the wavelength. Well, that is also there. That's also there. Also learn a little bit about the X-ray tube and how it works. That's how to label it all with the heater, the vacuum, the lead shield, things like that. And who discovered them? Who discovered X-rays? You can look that one up. I'm not telling you. Ha ha.